Last time we looked at in experiment 8 at how capacitors could slow down a relay oscillator. We're going to continue our experiments with capacitors today in experiment 9 of Make Electronics 2nd edition by Charles Platt. Following along with figure 280, which is a circuit diagram, there's switches involved. So each configuration of whether a switch is pushed or not needs to follow separately on the circuit diagram. So first through the resistor, and then through either the capacitor to ground or through a second switch labeled B directly to ground. This circuit is going to allow us to practice probing with the voltmeter. So I'm going to leave the black lead of the voltmeter in ground. I have the voltmeter in voltage mode, DC volts. And I'll move around to different parts of the circuit with the red probe. There I'm checking out the battery on the rails is just over 9 volts. Same configuration as before. Again, that LED at the bottom is one I've just permanently wired on as a check. I'm now going to move the voltmeter to the position that is suggested in figure 2-80, which is across the capacitor, or between the resistor and capacitor, and then the capacitor and ground. Let's look how this circuit behaves. When I hold the button on the top, I see the voltage across the capacitor begin to increase. It increases rapidly at first, and it slows down till it very slowly reaches its maximum voltage, very close to the rail voltage of about 9.3 volts. The moment I press the B switch, the voltage across the capacitor drops to 0. Let's try that again. It rises quickly and much more slowly as the capacitor charges. And discharging it by shorting the top of the capacitor to ground. Let's swap in another resistor. I'm going to remove the 1K that is suggested and replace this with a 5 kilo ohm resistor. Again, measuring across the capacitor. Charging, discharging, charging. Start slower and stay slower, taking a lot longer time to reach the full charge. Looks like it'll eventually get to 9.3 volts, but I'd probably have to wait quite a while. Just crawling here at the end. Again, this is a 5 kilo ohm and a 1000 microfarad or 1 millifarad capacitor, the biggest you have. And discharge. Again, straight down to 0. Now when you repeat this, you want to do it with a timer on hand so you can measure how long it takes to reach the maximum voltage. Try to record the numbers at some consistent interval every second or two. The textbook goes through several great procedures for doing this, and you'll be doing it on the assignment today. And charging takes some time. And discharging is immediate. So let's talk a little bit about why the capacitor holds charge. In this case, it's holding 1.7 volts. The textbook author suggests a capacitor is like a water balloon. Now, there's some pressure behind the pipe, of course. By now we associate it with voltage. There's a diameter of pipe or a size of a valve. That's the resistance in the circuit. And then the capacitor now is this balloon that's storing charge. And so we imagine that with more pressure or lower resistance, we fill the balloon faster. And the bigger the balloon, the longer it takes to fill. So smaller capacitance or smaller resistance leads to quicker filling at the same voltage. This proportionality relationship is expressed that the time to fill is proportional to the product of the resistance times the capacitance. Again, if you fill, or in fact, if you discharge that balloon, it will take a different amount of time. Now we're going to look at the FET capacitor simulation. First, on the basic capacitor part of the laboratory, you see we've got a battery hooked by a switch to a capacitor. Now we can't take apart a capacitor, so instead I'm showing you what happens inside a capacitor. In fact, you could take apart a capacitor, but it tends to get quite messy. So we're just going to use a simulation to visualize what's inside. We'll be doing this next lesson also with transistors. The charges are visualized as coming out of the top of the battery and then filling up those plates. And depending on whether I point the battery positive or negative determines which side I get positive charges on. But now notice there's something new in our model. Our flowing water model doesn't quite hold. We now imagine we have both positive and negative charges. So this is a bit of a beginning of a sophistication to our current flow model to now imagine what actually both positive and negative types of charge flowing through a circuit potentially. Notice how the positive charge on one end of the capacitor induces a negative charge on the opposite parallel plate, and that the value of the capacitance, the size of that balloon, is changed by altering the separation of the plates. As we increase the separation, the capacitance goes down, and as we decrease the separation, the capacitance goes up. As we make the plates larger in area, the capacitance increases as well. The capacitance actually stores charge, so just like a water balloon, I can remove it from the faucet, in his case by throwing a switch, and it keeps charge on those plates as long as I don't let it flow out. And capacitance is a value that has to do with the device itself, just like a resistance characterizes a resistor. Capacitance in farads, or capital F, is a metric unit of capacitance, and capacitances tend to be quite small. Picofarads, which is 10 to the minus 12 farads, nanofarads, microfarads, and in our case today we'll be using a very large microfarad capacitor. The voltage on the plates will depend on the voltage of the battery unless you take the capacitor off and start connecting it to other circuits. Again, really understanding it requires that we sort of have this idea of both positive and negative charge. Now we're going to make a circuit which has sort of got like a double throw switch. We'll be mapping out on the bar graphs up here not just the capacitance, the system in picofarads, but also the total charge in coulombs, more about coulombs to come, and the store energy in joules. So the moment I energize the battery, pushing positive charge one direction, negative charge in the opposite, I could disconnect it, and now I'm going to take it and flip the switch over to its other contact position, running it through a light source. And notice how all that charge just ran out of the capacitors and ran through the light source. Charge back up, disconnect, and the charge just runs up and around, but then eventually is gone. Notice how these different quantities change in the FET simulation. We're now going to hook our voltage probes up across the capacitor. And when we connect, notice that the stored energy, the stored charge, and the voltage across the capacitors all drops as those currents run through the light source. And try it with different configurations. Same voltage because it's the same battery, but with more capacitance, the plates closer together or the plates larger, it stores more charge, and the light source glows for a longer period of time and brighter. I encourage you to play with the simulation a bit. In the second part of the video today, we're going to look at the circuit in figure 2-86. Again, it's got both an A and a B button, but the configuration is a little bit different. The LED is now attached to the bottom of the capacitor. That's the negative side with a 470 ohm resistor towards ground. And the B switch, when the A switch is open, is going to connect the top of the capacitor, the positive end, to ground, at first using a 10 kilo ohm resistor. So like before, we kind of expect that A charges the capacitor and B discharges the capacitor. But A now, actually when we press it, although it's charging the capacitor, it seems to cause a current through the LED on the other side of the parallel plates. It's brightest when we first push it and then dimmer. And then in order to repeat the experiment, we actually have to hold down B for a while to make sure that the capacitor is fully discharged. And it's in charging the capacitor that somehow the current jumps across the parallel plates. And this is evidence that that simple fluid flow model just doesn't work. when we are talking about components that have voltages changing in time, like capacitors. Let's look at this circuit diagram in a little bit more detail. Again, the surprising result, in a sense, is that when we hold on the A button, the LED initially is very bright and then grows dimmer over time as the capacitor fills up. So we're left with the conclusion that there must be currents both going into the capacitor from the positive side of the circuit and also leaving the capacitor right when things change quickly. And it's only as the capacitor fills that the displacement current, as the author calls it, stops existing. That is the negative charge rushing in the opposite direction, which actually looks like a positive current. Initially, it's very strong as the capacitor fills quickly, and then tapers off slower and slower as the capacitor fills. And of course, B just resets the circuit. We're going to end today's video with a discussion of the time constant, the amount of time it takes to charge up the capacitor. And the idea here is of negative exponential dependence. And the idea is illustrated by figure 2-82, where we have a chef who's always going to eat the same fraction of a cake. If he eats 1/3 of the cake the first time, and 1/3 when he comes back a little bit later, and then another 1/3 and another 1/3, each time he gets less cake, there's less remaining, and the remaining slice gets smaller and smaller. When you graph out the voltage across the capacitor as a function of time in seconds, so again, you're measuring across the capacitor as we showed with a voltmeter, and you're measuring that voltage, say, every second or every 2 seconds and plotting it on a graph, you should be able to see exactly the kind of relationship that we observed in the first part of the video, with the voltage increasing rapidly at first and slower later on. That is, the piece of the pie gets less and less and less, but you never quite finish the entire dessert. How can we quantify this? Well, as we noticed in our first experiment in this video, the time that it takes to charge seems to depend on the product of both the resistance, that is, the size of the pipe that's allowed to let charge in or out of the capacitor, and the size of the capacitor itself at a particular voltage. And it turns out by multiplying R and C, that is ohms times farads, if we're using the metric unit of capacitance, the farad, which conveniently is the one that's written on our capacitors, that ends up giving you a time in seconds, the metric unit of time. Again, an ohms times a farad is a second. And that time is the amount of time it takes to reach 63% of the total voltage. If we take 63% of 9 volts, that gives us 5.7 volts. That is 0.63 times 9 equals 5.7 volts. And that would happen at 1 kilo ohm times 1,000 microfarad, which is 1 second. And we notice on this plot, there's a dot right at 1 second. We have just under 6 volts. I'd like you to follow up with that on the assignment for today. To start off, we're going to do a little bit of circuit building practice. I'd like you to build a circuit diagram that's equivalent to the one in figure 286, that's the LED lighting showing the displacement current. Now you notice I built it using one set of holes and wires on the breadboard. That's a bit different than the way that the author shows in his accompanying figure, which was figure 2-85. I'd like you to try to build it at least one other completely different way. In other words, the same circuit diagram, but implemented in a different manner, that is with a different physical arrangement of where the switches, resistors, and the capacitor are located on the breadboard. Same schematic, different way of building it, different than either of the two ways I've shown you. Place a picture of it with the LED on during those first few minutes, first few seconds when you have the button A pushed, and put that in your logbook. Next thing I'd like you to do is some exploration of the time constant effect. I've got 2 additional configurations I'd like you to build, and then using a stopwatch, plot out the voltage as a function of time. For both A and B, identify where on your graph those time constants are located. That is, what is the time given by RC, resistance times capacitance in the appropriate units, and what is the voltage at that time, and indicate those on both of those graphs and make sure that it approximately matches up. Finally, I'd like you to try to explain a rule of thumb that I use to think about capacitors, which is that they act as short circuits for changing voltages, but they act like an open circuit, as if there is no circuit component there at all or a broken wire when voltages are steady. Explain why you think this is and what evidence you've seen that supports my rule of thumb for the behavior of capacitors in circuits.